Hello. Now we want to see how much can we extract from these field theories without doing the perturbative expansion, right? This is in Peskin's chapter 7 and in Weinberg's chapter 10. Of course, Weinberg does it much more formally right from the start with a lot more generality, but that's not the path we're taking here, right? We'll start with the simplest examples and build up to the more general ones. Right, and that's very similar to what we do, what Peskin does in his book, right? So the very simplest green function we can imagine, right, is a two-point function of a scalar field, right, which would be something like a vacuum-to-vacuum transition of the time-ordered product of scalar fields, right? Not only I'm taking the simplest green function, but also the simplest field. And I'm not assuming anything about the interaction, right? This is an interacting theory. I'm not doing perturbation theory, so I'm not assuming it's weakly coupled or it's strongly coupled, right? And I don't need to talk about the interaction to do what I intend to next. Right? So what I want to build for this theory is a Hilbert space. Right? And for that I'll use two operators, the Hamiltonian and the vector momentum. Right? So I want states that are eigenstates of these two, and I would name those states by lambda p. Lambda p. This can be a little confusing at first, because depending on how you define this vector momentum operator, it won't commute with the Hamiltonian, right? In general, interacting systems, for interacting systems, these two operators do not commute. But it gets really simple if you think about what kind of states I'm including here. So there's basically three options, right? You can think of a single free particle, right? And of course, this is a state which is has well defined energy and momentum and three momentum, right? So this one is okay. Right? The second option is you have a system of interacting particles, right? In this case, I'm assuming this single particle is isolated from everything else. In this case, there are many arbitrary number of interacting particles, and they are forming a bound state. So this bound state, if you think of it isolated from the rest of the universe, right? It also has a well-defined energy and a well-defined momentum, right? Which is the total momentum of these particles here. And of course, the energy, you have to take into consideration the mass of this bound state will take into consideration the binding energy. So it won't be just the sum of the masses of these particles inside. And the third class of states is again a system of an arbitrary number of particles, which are in this case not bound. Right? So the total momenta of the system is still well defined, right? And also the total energy is just the sum of the energies plus whatever interactions is going on here. Right? What is not well defined in this case is the mass, right? So for this state, there is a number which is just the sum of masses minus any binding energy, and for this one, there's not, right? Energy can vary independently of momentum, because you go to the rest frame of the system, the total momentum will be zero, right? But energy can be anything depending on how fast these particles are moving, right? If you're convinced yourself that these three kinds of states can describe anything, right, then I have a complete set of states with which I can build a basis for this theory, right? In order to work with those states, I'll do an extra step, right? I'll define lambda 0 as these eigenstates of energy and momentum in the rest frame. So these are the zero momentum states. So they satisfy this condition equals 0, right? So these are the zero momentum states of these three types, right? And of course, then the eigenvalue under the energy operator I'll call E0 of lambda, right? And I'm using this lambda to count every other property of possible of the states. Of course, in the case of a single scalar field, there are not many, right? So this lambda will just run over possible masses, right? So, of course, I can obtain now any state of the theory doing a boost, right? I can take these states in the rest frames and boost then to arbitrary momentum, right? I do a boost to momentum p, right? And that's how I get lambda p, right? Of course, by Lorentz invariance of the Hamiltonian, right? I can say that these are also, the boosted states are also eigenstates of the Hamiltonian with some energy that I'll call, so this is lambda p, the energy will be EP lambda, right? And the eigenvalues of energy and momentum are related by the relativistic dispersion relation, right? So EP of lambda, right, is equal to the square root of P vector square plus M lambda square, right? It's important to notice that this works effectively, right, as a definition of mass, right? This is the real definition of mass in a relativistic theory, right? Is how momentum and energy relate to each other, right? This will coincide with all the definitions of mass you're used to for these first two cases, of course, right? If I look at a particle sitting in this rest frame, the energy is equal to the mass, right? Same for a bound state, right? If I look a bound state just sitting in this rest frame, the mass will be given by the energy minus individual energy minus individual masses minus binding energy, right? In the case of this third class of states, right, m lambda is now essentially defined as the energy of the whole system in its rest frame. So it's not what we usually call mass, because this is, as opposed to the first two cases where this is just a number, right? This is actually a continuous function, right, of the individual momenta, not of this total momenta, but of the individual momenta, of their positions, of the strength of interaction between these particles, of many things, right? But it is a complicated function of the properties of the system, right? Which in the case of a bound state is all encapsulated in the binding energy. We can get a clearer picture if we put those two eigenvalues in a plot. So let's assume for now that the lowest lying state is just a single particle with mass m1. So we are in this point, right? Energy is m1 and momentum is 0, right? If I boost this state, right, every other state connected to this one will be in this hyperbolic curve right here, right? That goes to energy equal momentum when I can ignore the mass, right? If I keep increasing the energy of the system, eventually I get to the point where I can produce two of these particles. So I'm sure there's also a point here somewhere, right, which is a state with two free particles, each with mass m1, right? And that state has energy 2m1. And again, I can boost this, and states that are produced by this boost are lying in this other hyperbolic curve right there. The thing is, a different thing can happen, right? Before I get to this state of two free particles, I can have bound states, which will have their own masses here that I'll have to label like M2 or M3, And each of those states will have its own hyperbole, right? So I have kind of a discrete set of hyperboles until I get to this point. What happens above this point is that I can populate any point here, because now I have two free particles, right? And they can have essentially any combination of energy and momentum, right? I can still define a m lambda for each of these points along that line, right? And then boost it everywhere else. But this is now a continuous thing, right? It goes continuously. I can populate any point along that line, right? And of course, the same happens again if I think on the point that I can produce three free particles. So this is 3m1. I'll have an hyperbole that goes up here, right? And possibly bound states of three particles and yet another continuum above that curve, right? Those considerations are important if you want to write a completeness relation for the Hilbert space here, right? Let me just delete this so you have a clear view up there. Try to draw a hyperbole by hand. There, it's not good, but it's okay. Okay. And my completeness relation will look like this, right? I have an identity, which is the sum of all the possible states. I start with the vacuum, right? And then I have a sum over lambda. But in some regions, this will not be really a sum because I can vary m lambda continuously, right? I'll try to indicate that by this strange notation right here. Sometimes I'm doing a sum in lambda, sometimes it's really a continuous varying of lambda, right? I won't need to specify if it is a sum or an integral for a while. So for now, I'll just leave it like that, right? And then I have a completeness relation for the eigenstates of 3 momentum. That I'll write like this with the same relativistic notation that we have been using in the quantum field theory 1 videos, right? So this is what my completeness relation looks like. Sometimes with lambda varying discretely, and in other places really it's just a continuum variable that I can change. Now let's go back to our 2-point function, right? The green function we want to understand, right? So we're looking at the vacuum-vacuum transition, right? With this operator in the middle. And let's assume for now some time ordering, just to simplify our lives. We can do the other time ordering later. So for now, let's assume x0 is bigger than y0. That means this is equal to omega phi of x, phi of y omega, right? And now I will insert this identity in here. So just put my completeness relation right here in the middle of those two. So this will equate this one. So I'll have, I'll have this to the left, this one to the right, right? And in the middle, I have to put that identity. So I have omega for this first part, omega, that same thing. Let me copy it over here, plus this one again. And now I have to introduce this one right here, right? So just put this here, this one there, and now make everything fit on the screen. So I have this first term, which involves vacuum expectation values for these fields. Remember, these are all operators, right? And then this complicated object here, which I'll have to treat carefully. Right? The first consideration I want to make is that these vacuum expectation values are zero. Right? This is not always true for all theories, as you might have seen if you have spontaneous symmetry breaking. This vacuum expectation value can be a number different from zero. But what you usually do in those theories is shift the theory to a new field, which actually has a zero vacuum expectation value. And then you deal with the consequences of that, like the Higgs mechanism or Goldstone bosons, whatever, right? We assuming this has been already done. So if there is a spontaneous symmetry breaking going on, we are already in the broken phase. So we already made that shift. If you don't know what I'm talking about, don't worry. We'll just assume this is zero, right? And move on. Right? So next step is deal with these two matrix elements right here. Right? So now my green function is described just by this part because the other one is zero. Right? And I want to deal with these matrix elements. Let's take one of them, and then we can do the other by analogy later. I'll do a very similar treatment to both. So what I can do here is first do a translation. So I want to move this field to the origin, right? And I know that the generator of translations is the momentum operator, the tree momentum operator. So I can write this as the exponential of I p x phi of 0 exponential of minus I p x, because these exponentials here are the transformation that takes the field from 0 to x, right? If I plug this in here, right, I'll get omega times all of these lambda p, right? Now, the moment of the vacuum, right? Now I'll act with these operators in here and over there, right? So this acting there, the moment is 0, so this is 1. And this one acting here, since this is an eigenstate of momentum, I can just remove the operator and replace it by its eigenvalue. And then P0, right? The energy, because this is a for momentum, right? The energy here, in fact, I said 3 momentum when I said, but this is always for momentum, right? It's a shifting space-time. But the energy here is just P0, so, and we will satisfy the relation above. So I get omega p of 0 lambda p times the exponential of minus I p x. With, we can't forget, p0 is just e p. Right? So now what I want to do is move this back to the rest frame of this state, right? So I want to make a boost back to the rest frame. So then that can be done by a unitary transformation that I'll just call U. So I'm saying that I'll define some transformation U that acting on lambda p takes me back to the rest frame. Right? So it's the opposite of the inverse of the boost that defines this guy from this guy. Right? If I take this transformation and insert it here, so I inserted this in two places, here and here. So for the first one, I'll just put u minus 1 u. Then for the second one, again, u minus 1 u. EP. And this, I know how to calculate everything here. Right? So for instance, this is how I define u. So this is just the state lambda 0. This is a scalar field, right? So it does not transform under boosts. That goes to phi of 0. And of course, I have to assume, otherwise I would break Lorentz invariance, that the vacuum is invariant under boosts. Right? This is an important part here, right? Eventually this is very simple for a scalar field, but eventually I want to generalize these for other fields or even operators. If you look at Weinberg's book, he's doing a very similar thing right at the start of chapter 10. But he's using just any product of fields or derivatives of the fields here. Just a very complicated generic operator. As long as I know how the operator that is in here for the green function I'm calculating, if I know how that operator transforms under boosts, then I can do what I'm doing here, right? Of course, it will be a little bit more complicated because you have some kind of representation on how the field transforms. But these matrices that can appear here, they'll go out of this matrix element, and with very little change, I can do everything I'm about to do. So keep that in mind. We're doing for the scalar right now, but that's not very hard to generalize as long as I'm using something here that I know how to transform under boost. So it could be a spin or it could be a spin one field, but it could also be more complicated operators. As long as I know how they transform under Lorentz transformations, I'm good, right? So for the scalar, that's very simple. I can write now that this is equal to omega phi 0 lambda 0 times the exponential of minus IPX P0 equals EP. And now I can go back to the expression above, right? I can go here and put the expression I got below for this guy. Of course, this one is very similar, just the complex conjugate and exchanging x by y. Right? So in what I get, right, is this. I'm the vacuum transition of phi x, phi y is given by this sum or integral over lambda and the integration over momentum. So this one, the integration over momentum, normalizations, times this guy, but twice, right? Because this is just the part between omega and lambda p with the operator phi of x, but I also have this part over here, right? So what I get now is this element times its complex conjugate. So I'm getting omega phi of 0 lambda 0 square, right? And then the exponentials, right? With different signs, and in this case is with x, and the other one is with y. So I get these exponentials, and I'll separate the time and position parts. So I have exponential of I p x minus y times the exponential of minus I e p x0 minus y0. The reason I'm doing this separation is because I know that this integral, if I take a look, let me go up a little bit. If I take a look at this 3 momentum integral, I'll quickly recognize that I can write this as a 4 momentum integral, right? So I have I p x minus y exponential of minus e p x0. In my convention, the 0 can be up or down, it doesn't matter, because of the metric I'm using. Lambda. This is the same as doing this integral over by using residues, right? So I take x0 bigger than y0 because of the path of integration I'm choosing, but I can write this as the 4 momentum integral of I p square minus m lambda square plus I epsilon, right? This is the Feynman's prescription for the pole, right? And then I have the exponential of minus I p x minus y. And this is everything here is the 4 vectors, right? You will recognize these. We have seen this integral done many times in quantum field theory 1. And of course, what appeared here is just the Feynman propagator, right? So if I go back in this expression with this new integral, I can write that. Let me copy almost everything here. So what I found out is that I can write this now as d4p 2 pi to the 4th. This goes into the normalization. That guy stays there, and I get I p square minus m lambda square plus I epsilon. And here is the exponential of minus I p x minus y. Right, so that's the result for this time ordering. Remember, I choose a particular time ordering. Now I can do the same for y0 bigger than x0, right? Of course, it's just the same again, right? Just replacing x for y everywhere after I do the ordering, so no news there, right? And I'm getting to the conclusion that I can write the 2-point green function in that case, right? With the time ordering here. I just have to put together these 2 time orderings that I did. It will be equal to and I can use this, right? This is a Fourier transform of the Feynman propagator. So what I have here is the Feynman propagator in position space, right? So I get this new thing over here, and then df x minus y m lambda squared, or m lambda, that depends on how you want to write it. So this is the important result we wanted, right? This is a fairly interesting expression, so let's stop and think a little bit about it, right? Suppose we are far away from the region where this lambda becomes a continuous variable, right? So we are in that part where you can produce single particle state and then some bound states above it, right? And I can look at this just like a sum instead of an integral. Right? In that region, what I'm getting here is basically a sum of Feynman propagators, right, for different values of m lambda. So I'm seeing something like propagator from x to y for some state that I'm labeling lambda 1 and with mass m1, plus some other Feynman propagator also from x to y, or y to x, doesn't matter if scalar fields, which I'm labeling, say, lambda 2 with mass m2, right, with some weight in front. So these are numbers, right? This is just real numbers equal or bigger than 0, right? So there's some number in front of it, some weight for the contribution of these many different possibilities, right? And this is in a theory with a single field in the Lagrangian. I'm just using the simplest thing with just one scalar field in the Lagrangian. But still, I'm getting this sum of many poles, right? Each of these Feynman propagators will produce a pole for a different value of m lambda. So m1, m2, so on and so forth. If you think about this in terms of Feynman diagrams, right, it is like we have this propagator starting from x, something happens, right? In this case, it's just one particle, right, and y. But in this second case, is more like you have intermediate states of I don't know how many propagators, right? That goes back into y somehow. That what goes into these bubbles depends a lot on the particulars of the interaction. But these bound states are also producing poles in this green function in different places. Even this m1, right? Our tendency is to think, well, this m1 is coming from something in the Lagrangian, right? Which is just m1 square phi square over 2. But not even that is guaranteed, right? If you think where m lambda showed up for the first time, right? You go back right here, where I exchanged this 3 momentum integral by the 4 momentum integral. This is the first time m lambda appeared, right? But it appeared here because it was hidden in here, right? EP is equal to the square root of p square plus m lambda square, right? So this m lambda is not defined from the Lagrangian. In fact, it could be the same number as the one in the Lagrangian. It could be a different number. We don't know, right? What we know is that this is the physical mass of some on-shell particle because it's defined by its this relativistic dispersion relation, right? That's how m lambda showed up for the single particle state and for the bound states. So this is really a physical mass, right? And what we're seeing here is that all the interactions between those lines here, which are very complicated, whatever they are, they will produce poles in this green function if this is a bound state. Of course, this is more complicated once we go into the continuum of lambda, but for the discrete part, right, where you have these discrete bound states, this is pretty clear. I'm producing a lot of poles in the green function, even if I have only one mass parameter in the Lagrangian. And none of these masses, M1, M2, M3, so on, right? None of these masses are directly related to that mass in the Lagrangian, that mass parameter in the Lagrangian. So this is one of these instances, the first instance where we see that if you go to a more complete version of the theory, that relation between the masses of resonances, the masses of the particles you actually see, are not easily and straightforwardly related to the one in the Lagrangian, right? We will go back to this later. It is very useful to rewrite this expression by introducing a new integral. So what I'll do is take this thing apart here and introduce a new integral over the m squared. So m has dimensions of mass. I'm integrating over m squared, and this 2 pi is just for convenience. I'm integrating this from 0 to infinity. And of course I have to, since I want to go back to the previous expression, I have to introduce some delta function here somewhere. So I'll just put a 2 pi here. Again, this 2 pi is just convenient, right? Dirac delta of m squared minus m lambda squared, which allows me to replace this m here by m squared, right? I could indicate m lambda or m square or not, but the thing is I'm exchanging. I know this mass only appears squared inside this propagator. Right? So if I do some reorganization here, I can move this sum over to the left. The 2 pi goes here. And this is the object I want to keep track of. And I'll give a symbol to it. So I'm defining, right? This is just a function of this big m squared, since I'm summing or integrating over lambda, right? Which I'll call rho of m squared, right? So I'm defining this object to be this. Which is called the spectral representation, right? The spectral density, or this name is Swedish. People avoid pronouncing it on videos. I think it's pronounced Källén, or Källén, or Källén. Lehmann spectral representation. Right. So this function is very important because it encodes everything that the theory does, right? So it's basically, as we've seen before, right? We're basically summing over these intermediate states. If they are bound, you're just producing these simple poles. If they are free, then you have some continuous variation of m lambda. But in any case, all the information of what states appear and how they are localized, right? So the spectrum of the theory is contained in this function, right? Which, of course, is not easy to calculate, right? So let's take a look, right? I can plug this back in to the expression I had for the green function, which now becomes much more compact, right? So this is just the integral over this big m square parameter over 2 pi of the spectral density function, which tells me where the resonances are, where the continuums begin, right? The continuum of 2 particles, the continuum of 3 particles, if they are there at all, right? And then this serves as a weight for the contributions of these Dirac propagators, right? Which also depend on this mass. So this makes very explicit the fact that you're running over these mass scale and looking for poles when this is a discrete sum, or we'll see branching points when lambda becomes continuous. Right? Now let's look, since we have this expression here, right? Let's look what happens close to the one particle pole, right? If the theory is capable of producing this single free particle, right, which is related directly to the field in the Lagrangian, right, then I'll have a pole in this mass that I called M1 so far, and let's see how this behaves close to that pole. So right there, the spectral density will be dominated by lambda, right, by the very first mass. So close to that one particle pole, this sum will be dominated by m lambda equal m1, right, the very first resonance. Right? For short, now I'll just call this m. Right? And so this expression, 2 pi times the delta of m squared minus m lambda squared omega phi 0 phi of 0 lambda 0 modulus square, right? Close to that pole, it will behave like just 2 pi delta of m square minus little m square, right? I'm suppressing the 1 for short, times omega phi of 0, the one particle state at 0 momenta, right? Square. And I'll call this is just a number, right? Which I'll call for now z, right? So what I'm seeing here is, if I go back with this right here, what I'm seeing is that this guy will become just so I put whole row of m square here. Well, let's replace this by 2 pi, which conceals this 2 pi right here, delta m square minus m square, little m square. This is close to that one particle pole. Let's call this one particle, right? Of z times this guy. Of course, now I can do the integral, right? And write this explicitly. So this will be equal to d4p. This is just, I'm explicitly writing this position space propagator over 2 pi to the 4th I z, right? Let's not forget there's a z here, over p square, right? I can use this delta and just do this integration. So I just replace big M by little m. So in the propagator, I'll just have little m square here, plus I epsilon exponential of minus I p x minus y, right? Which is very important result, right? So near, what I'm seeing here is that near the one particle pole of this theory, the 2-point function behaves in a very similar way to the free particle, in here free theory, right? And here we have to be very careful about making the difference between free particle and free theory, right? When we say free theory, it's really a Lagrangian without any interactions, right? Just a Gaussian on the fields. When we say free particle, we can mean very, depending on the context, right, very different things. You can say free particle meaning a particle from a free theory. Well, this is really a free particle. It doesn't interact with anything. Nobody will ever see it because without any interactions, there's no measurement, right? But you can be talking about a free particle of an interacting theory. And then you mean a particle that is distant enough from all other particles that it is behaving as free, right? It's moving in a straight line, right? So this is the propagator of a free particle in an interacting theory, right? This is the green function near that pole where I have the contribution of just one particle, right? This motivates a lot of definitions right here that we use a lot later in the renormalization program, right? So we call this Z, this, which will be very important. This is the field strength renormalization. Z will be the field strength normalization. This mass, by the way, we got it, right? Please pay very close attention to this, right? So this mass was obtained from the relativistic dispersion relation, not from the Lagrangian, right? So this is what we call the physical mass, right? Because it will really be a pole. When I put a particle on shell, this is the mass it will have, right? And I'll now change my notation, right? If I ever write a Lagrangian, so far I'm not even worried exactly what a Lagrangian is. But if I ever write a Lagrangian, I'll call that mass parameter that appears in the Lagrangian M0 from now on. And that's the what we call the bare mass. Bare in the sense that this is the mass that would coincide with the mass for a free particle in a free theory. So it's the particle undressed, I mean separated from all these things that it carry along itself, right? So if you think of an electron, there is no physical meaning in which you could talk about an electron without considering the electric field or the magnetic field caused by the movement of this electron. It is some charge plus the fields around it, right? So this is the mass the electron would have if you could remove all this dressing that goes around the electron, and this is the physical mass. Right? A lot of these interpretations will get clearer as we go on. So for now, these are just names. The important thing is to keep in mind that we went with this non-perturbative procedure here straight to something that is very closely related to a physical thing that I measure. That's the physical mass. It has nothing to do, or at least a priori, no relation to the one in the Lagrangian. Of course, we'll have to find a relation between them if we believe that the Lagrangian contains information on how to get this guy, right? But we'll get there eventually. Now, suppose I do just a little change in my field variable, right? I just define a new field by this. I just call this just phi prime. Phi prime. It's not the derivative, it's just another field, right? Which I'll define in this way. I'll just take phi and divide by the square root of z, right? Just very simple change of variables, right? Just a rescaling. I don't know what z is, but supposedly I can calculate it. Right? If I go back and substitute this here and do everything I did so far, nothing will change, right? The square root of z will just go out and sit there through the whole calculation. And the result will be that this, if I calculate the green function for this new field, omega t of phi prime of x, phi prime of y, omega, in this case will be near again, near the one particle pole, will be given by this, d for p, d for p, 2 pi to the fourth, I b square minus m square plus I epsilon exponential of minus I p x minus y. Right? And here I have something very curious, right? So by redefining my field, renormalizing my field, if you will, right? I got a new field that has near the one particle pole exactly the same analytical form as you had for a propagator in the free theory. Just now the pole has moved. Remember, m square is not m is not m0, which is in the Lagrangian. So for free theory, that pole would be at m0 with this residue, right? Now the pole has moved, but I kept the same form, right? We'll see that we'll do this again and again, and this is the very essence of what is renormalization. I'm trying to write my theory in terms of fields that better reflect the physical states, right? So that if I make the analytical properties of these guys similar to what I had in the free theory, right? I know that a lot of the conclusions I had before when I looked at asymptotically free states and all, right, will be very similar, but now exchange this bare mass that showed up in the Lagrangian for the physical mass. Everything else looks very similar, at least for the one particle states, right? So what I'm trying to do is rewrite my theory in terms of fields and physical masses, and we'll see soon also couplings that are more, which are closer to the observable ones, right? And notice, please, I didn't do a single loop calculation yet, right? I'm not even assuming the theory accepts a perturbative expansion where those loops will show up. So this is a very general result, and shows us, is the first hint that renormalization might be needed or useful, even if there were no loops or infinities in the theory. Right? That's a very important point, because most books start the whole renormalization discussion by trying to calculate a loop. Right? They are very loosely related. Right? Renormalization will solve problems that we have when we calculate loops, but it's not a consequence of those problems, right? Renormalization is a way to make more explicit physical information in your theory, right? Now we can look also at, right, here I just looking at close to the one particle pole, but I can look too for what happens away from that pole, right? And in that case, it's useful to define another quantity. So I take the spectral function and rewrite it like this is a definition. Right? I'll rewrite it as the single particle pole, right? That one I was just looking at a moment ago. Here's the field renormalization, right? Plus everything else. Right? It's not very rich definition so far. But the thing is, we know a lot about this guy. We can prove a lot about these guys, right? The general form of this thing will be something of this sort, right? We can just plot the spectral density against this mass square parameter. And the general form will be the following, right? You have some delta function for the one particle pole, right? This will be just some, let's represent delta functions like that, right? And then, of course, if you have bound states, you have a few other poles like we explored before. I'm changing the height because they have different weights in front of them, right? But then you enter a region where you can vary these continuously, right? Once you hit twice that mass square, right, you have some complicated function, which could have any form, right? So this is encapsulated by sigma, right? All these, both the resonances that could be at different masses, right? You can call this M2 square, M3 square, right? And this continuum, which I'll just label lambda tilde. And so I can rewrite the green function, right? Let's take the Fourier transform of the green function. So d4x to go to momentum space, right? Exponential of IPX of the green function. Phi of x, phi of 0, just making y equals 0 to simplify the expression here, will be the integral of 0 to infinity the m square over 2 pi rho of m square I p square minus m square plus I epsilon, right? So I went to momentum space. If I substitute this here, right, and separate the part comes from sigma tilde from the whole sigma, right, what I'll get is something that looks like this, right? So the first particle pole, the one particle pole will just be, as we have seen before, p square minus m square plus I epsilon. There will be a bunch of other terms very similar to these with different values here instead of z, right? But the same kind of poles. So they're poles for the bound states. And finally, you have something that starts at 4m square and goes all the way to infinity, which is an integral now over a continuum continuous function, right? And of course, you can have bound states on top of these, right? If you ever looked at the spectra, or I don't know, hadronic spectra, you have seen some that looks like that, right? You could have three particle bound states on top of the continuum of the sigma, so could be very complicated. But in any case, you can write these as this integral of sigma tilde m square p square minus m squared plus I epsilon, right? So if I look at the analytical properties of these momentum space green function, right, you see that this part, right, will generate branch cuts, right? Because now I'm moving m squared, and this has a pole every time p squared is equal to m squared. But m squared is a continuously varying variable, right? So essentially the analytical property of this green function is something that on the complex plane, now I just take epsilon to 0, right, to move the poles back into the real axis, because I don't care where they exactly they are right now. But this will look like in the epsilon going to 0 limit, right? This will look like a pole in m squared, poles for each of these bound states. So here I have the bound states. And starting at 4m squared, then I have a branch cut for this function. So this is what the analytical, this is the imaginary part. This is a function of p squared, right? So this is the imaginary part of p squared. This is the real part of p squared. So that's how these green functions look, right? And of course, if you compare that with the expression of the momentum space green function for a free field, a free theory, right? That looks like this, right? Phi of x, phi of y. Now I'm exchanging omega for 0 because I use 0 to indicate the vacuum of the free theory, right? And you see that that would look like this. Which shows us that in the limit you go to the free theory, right? You have to take z to 1, right? And m to m0. You go back to this state and you lose all the bound states, you lose the branch cuts, right? All these is produced, is a result of the interaction, right? In fact, you can show very easily that that is shown on I won't do it here, but you can find it in Weinberg's section 10.7, right? You can show that these spectral density has a positivity property. Also, the integral of rho of m squared d m squared is 1, which is consistent with the fact that this is basically a weight for this, how much one particle and two particle and three particle states contribute. And also you can show that z plus the integral of sigma m squared d m squared is 1, which means that when z goes to 1, sigma has to go to 0, right? This integral has to go to 0 and all these bound states disappear. On the flip side, you can also think what happens when z goes to 0, right? When I don't have this single pole state, because if z goes to 0 up here, you see that the very first state disappear, right? This is the case when the theory is very strongly coupled, right? If you try to do the renormalization in that case, right? This phi prime will become just a huge field, right? Which amounts to integrating out this field. We'll learn better what exactly integrating out means soon. But that's the case when the particle, the field in the Lagrangian does not produce a particle, right? So, or whatever particle equivalent to that has no field in the Lagrangians. It's really composite state. But we'll go back to that. But of course, this case with z equals 0 is totally non-perturbative case, and it's very hard to calculate anything in that limit. Right? So this is just I'm trying to sum up some properties of the spectral density function, but the message I wanted to give today is already finished, right? So remember that once we renormalize the theory, once we change these field variables, we can make the physical properties more explicit. And that means going away from, it will mean going away from these parameters that we had in the Lagrangian. Right. So that's it for today. See you next video.